All right, this next one. For each addition, describe how the ratio of NaA to HA changes with each of these additions. So first off, this ratio, let's break that down, okay? What are we talking about? NaA. Well, Na is plus 1 charge, and A must be minus 1 charge, right? So what I'm really being asked here is, what is the molarity of A minus over the molarity of HA? And by now, you've probably developed a good eye for this. I think what they're asking us is the ratio of the base to the acid in this pH buffer. A minus is the deprotonated form, HA is with the proton, it's the base and the acid respectively. So for part A, we're told that we set up a buffer at a certain pH, and then we're going to add some 0.1 molar NaOH. What's going to happen? Well, this 0.1 molar NaOH is basically a source of OH minus, isn't it? If I add that to my buffered solution, I have to account for it. I have to do something with it. I can't just let it float around in solution, because if it does, it's going to affect the pH. It will change the pH. So what essentially happens is that because my buffer is a mixture of a weak acid and its conjugate base, the weak acid can work to offset this change of sodium hydroxide. The weak acid will react with the hydroxide, which is added to make water, thereby neutralizing the addition of hydroxide. And it looks like as a byproduct of this reaction, I'm going to make some A minus, won't I? So if I run that reaction, it stands to reason that this ratio of A minus to HA should what? Increase. The reason being, it's a direct byproduct of this first reaction. I'm making more of it, its concentration will increase. Meanwhile, I'm using up HA, aren't I? So part A, I'll certainly see an increase. What about part B? On part B, I'm adding some HCl. So what happens here? Well, if I add that to my buffered solution, remember my buffer is a weak acid with conjugate base, it seems what can happen is the conjugate base component, or the A minus form, can react with the protons, the H plus from the strong acid, to make HA. We'll also make chloride ion. So look what's going on here. Well, I'm going to make HA, aren't I? Well, I'm using up A minus. So again, if I want to think about this ratio of A minus, the base to the acid, respective concentrations, it seems like here I'm using up A minus and I'm making HA. So it seems like the number in the denominator is getting bigger and the number in the numerator is getting smaller. It seems like that ratio is going to decrease for this case. And we can justify it by this reaction, okay? Now maybe this problem seems kind of simple to you, okay? And now think about why I'm asking you this. I'm asking you this so that you know these reactions and you can rationalize what happens when you take a buffered solution and you add a strong acid or a strong base. That's the purpose of this question, right? I'm basically tutoring you on that. How does the buffer offset the change of a small amount of acid or base? You need to know these reactions to explain that. And that was one of our key learning objectives, wasn't it? All right, let's go on and talk about C and D just real fast since we're on this problem. What about C? Here we're going to dissolve some what they call NaA. Now, remember back to general chemistry, when you make ionic compounds, you need a cation and an anion, don't you? That's what's going on here. It's the sodium salt of our conjugate base. When we throw that in water, it dissolves, just like sodium chloride would, to produce A minus. Since we're producing A minus by the dissolution of this salt, it makes sense that the concentration of A minus is going to what? It'll increase. Now, maybe the HA goes up a little bit in response to that, but I think here that ratio is bound to increase. And likewise, for D, it seems like we're doing the opposite in D. We're adding some HA, we're adding some of the acid form. So by adding some of the acid form, the denominator will increase, won't it? So the trend will be to decrease this ratio. All right, easy enough. Got to know those reactions. That's what's crucial.